Hi guys, today we are going to talk about some popular patterns used in building microservices architecture. Actually, there are a lot of them, but we will focus only on a few. In microservice architecture, we have interesting situation. Every service can be scaled horizontally and deployed in different environments, from dev to production. And here comes a logical question. How can we find the right service? And why we can't just hardcode the URL? This answer is simple. Services can change their addresses, scale up and down, and move around. So hardcoding does not work. That's why we have the pattern service discovery and service registry. In fact, service discovery is the procedure of finding a service among its copies. And service registry is like an address book where we store information, IDs, IPs, ports, and etc. How it works? First, when a new service starts, it registers itself in the service registry. It's like saying, I'm here, this is my address and port. Then if another service, for example service A, wants to call service B, it asks service discovery, tell me where is service B now. Discovery returns the actual address and can even provide load balancing to distribute traffic evenly. By the way, this is not only about HTTP, it can also be a RabbitMQ queue or a Kafka topic. Well, the mechanism is universal. There are two types. Client-side service discovery. The client asks, for example, a Eureka, Zookeeper, or Console. It gets a list of instances and decides where to go and how to balance traffic. And server-side service discovery. Here the client makes a request to Nginx or AWS ELB. The server-side component checks the service registry, picks an instance, and forwards the traffic. Okay, so the aggregator pattern is used to collect and combine responses from several microservices into one single response for the client. It works like an intermediate layer that makes the interaction between client apps and a complex microservice infrastructure much simpler. Let's take a closer look at the problem this pattern solves. Data aggregation. Instead of the client making multiple requests to different microservices and merging data itself, the aggregator handles it on the server side and returns one complete response. This reduces network load and simplifies client logic. Protocol diversity. Different microservices may use different protocols like REST or gRPC. The aggregator can translate them into a single protocol convenient for the client. Like for example REST. Tight client coupling. Without an aggregator, the client must know each microservice's address and protocol, making client code complex and sensitive to backend changes. Okay, now let's talk about the API gateway. It is a network gateway that serves as a single entry point for all external requests to your microservice architecture. By the way, it is important to understand that API gateway can be an implementation of aggregator, but not the other way around. Why is that? Actually, the aggregator pattern only describes a general idea, a service that aggregates responses from other services. API gateway, in contrast, is a specific infrastructure solution with a wider set of tasks. Some key functions of API gateway include authentication. The gateway can perform the first user check. Login. It collects information about incoming requests and how they are perceived. Monitoring. It gathers metrics and traffic data, which is very important to understand system health. Caching. It stores responses for frequent requests. Request control. It allows setting limits on the number of requests to protect the system from overload. Traffic routing. It forwards incoming requests to the right microservices based on defined rules. SSL handling. The API gateway can manage SSL termination so internal services work with the plain traffic. This reduces their load. Typical implementations of the API gateway are Nginx, especially the extended version Nginx Plus, and cloud solution like Amazon API Gateway. Actually, it is also important to remember that the API gateway can become a single point of failure. To solve this, teams usually apply horizontal scaling and fault tolerance mechanisms. Now, let's move to the backend for front-end pattern. It says that each UI application, for example, a mobile or a web app, gets its own specialized backend. In fact, you can think of BFF as a type of the aggregator pattern. The idea is to create an individual API for every client app to meet its unique needs and optimize communication. Instead of one backend trying to serve everyone, each BFF is a small internal backend designed for a specific UI team. This makes it possible to handle the special requirements of each client, like different datasets to show or network constraints. And this really simplifies client-side development. By the way, this approach is very useful for multi-client web apps or products. For example, when a company has one common backend, but several UI with specific differences. Instagram is a good example. It has a shared backend, but different UIs. BFF collects these differences and lets team quickly deliver separate full UI solutions, while still using the same backend platform. Now, let's move to the proxy. It is a helper component that forwards requests between a client and one or several target services. Its main task is to provide controlled and secure interaction, especially when we work with third-party solutions. For example, imagine your frontend or even another microservice needs to talk to an external service like a payment system. Often, these integrations require sending an API key. Hardcoding the API key on the front-end side is a big risk. This is where the proxy is very useful. It can manage API keys centrally, hiding them from the client and adding them to outgoing requests. In this way, the key is stored safely on the proxy, not on the client. By the way, proxy can also give other useful features. It can cache long-running requests. If a response takes time to generate, proxy can store the results. Proxy allows us to track the total number of requests to an external service. This is important for paid APIs, so we can control costs. It can also add extra parameters to requests which should not be visible for the client. And finally, service versioning. For example, an old client called the old version of the service through proxy, while a new client calls the new one. This keeps backward compatibility and allows gradual changes. Well, let's look at the sidecar. It is basically a helper service or a component that runs next to the main microservice. You can imagine it like a part of a motorcycle. They always move together, but they are still separate parts. In Kubernetes, for example, this can be two Docker containers running inside one pod. The main purpose of Sidecar is to take over helper functions, so that the main microservice can stay simple and with less coupling in its code. By the way, Sidecar has many use cases. It is perfect for logging, monitoring, and environment configuration. Instead of making every microservice handle log aggregation and formatting, the sidecar can read logs from the main service, transform them, and send them to a central system. If later you decide to change the logging tool, for example from Kibana to Graylog, you only update the sidecar, not the main service. It can also provide secure inter-service communication, such as mutual TLS. The sidecar can take care of all certificate management and exchange, though the main microservice does not need to handle these technical details. Another common use is the client-side load balancing and circuit breaking. For example, Envoy as a sidecar can talk to the service registry and then balance requests between available instances. Actually, the main advantage of the sidecar is that it talks to the main service through localhost, not through the network. This gives high speed and reliable communication, because they run locally but still as isolated processes. It is important to understand that sidecar and proxy are not the same thing. A sidecar can use a proxy as its implementation, but sidecar is about how the component is deployed, and proxy is about what the service does. Now let's look at some ready-to-use solutions. The first one is Envoy. It is a modern proxy with support for load balancing, TLS, retries, and monitoring. By the way, it is often used as a sidecar in platforms like ISTO or Console Connect. Next is Promptail. It collects logs from containers and sends them to Loki. Another example is Vault Agent by HashiCorp. This sidecar automatically loads and refreshes secrets inside a container. And finally, the classic Nginx. It can be used as a sidecar reverse proxy for TLS termination or rate limiting. Now let's look at CQRS or Common Query Responsibility Segregation. As the name says, it means splitting responsibility between commands, operations that write or change data, and queries, operations that read data. This pattern is used when there is a big imbalance between the numbers of reads and writes. The main goal of CQRS is to optimize the system for different load profiles of reading and writing. For example, imagine your system has millions of reads requests, but far fewer writes, like YouTube. In this case, by splitting these operations, we can scale read and write components independently. Well, it also let us use different technologies for each site, choosing the best tool for the job. For example, for writes, you may use a traditional relational database like PostgreSQL. For reads, you may use a fast cache like Redis, a search engine like Elasticsearch, or even MongoDB with the normalized collections. Let's check a typical flow. The client sends a command, for example, create order. This command goes to the command service, which runs business logic and validation. After successful validation, the data is written into the write database, for example, PostgreSQL. After that, the data needs to be synchronized with the read database. On the other side, when the client sends a query, for example, get order list, this request goes to the query service. The query service reads directly from the read database, which is optimized for fast read. Well, for synchronization, we can use different mechanisms. In the simplest case, if the write database is the main one and the read database is just its replica, then synchronization happens automatically with the tools of the database itself. In more complex cases, when the writedb and readDB are different types of databases, we use a message bus or even broker such as Kafka or RabbitMQ. In fact, the system publishes events about data chains, and a special service like the read model updater service reads these events and updates their read database. By the way, another option is the change data capture approach. It automatically tracks changes in the write database and sends them to update the read database. Here we can use the tools we already know, Debezium. Actually, CQRS is a powerful tool, but like any architecture decision, it has trade-offs we need to consider. Among the advantages of CQRS, we can highlight targeted choice of technologies. By splitting reads and write logic, we can pick the best technology for each site. For reads, we may use Redis for super-fast access from memory, or Elasticsearch for full-text search. For writes, we may use traditional relational databases like PostgreSQL or MySQL. This flexibility allows us to use the strengths of each tool. Flexible scaling. We can scale reads and write independently. For example, if your service has far more reads requests than writes, you can scale read replicas horizontally without touching the write side. Simpler domain model. By splitting code into read and write parts, the cognitive load for understanding the service becomes lower. Using denormalized data. For fast reads, we can use denormalized tables or materialized views, avoiding heavy joins. This makes queries much faster, which is critical for high-performance systems. Lower risk of blocking. Since reads and writes happens on different models, CQRS helps reduce the risk of blocking write operations with read queries. But there are also disadvantages. More complex architecture. Having separate reads and write models increases the overall complexity of the system. It requires extra effort for management and support. Eventual consistency. One big challenge is that the read model is not always up to date right after a write. Synchronization is asynchronous, so data may be slightly out of sync. Code duplication. Even though CQRS aims to simplify, in some cases code duplication can appear and it needs attention during maintenance. So the decision to use CQRS should be based on a careful analysis of your domain model and non-functional requirements. Now I also want to talk about internal libraries. Well, they are not really a microservice pattern, but they play a very important role in building and connecting microservices. Their main goal is to reduce code duplication and make it possible to reuse functionality across different microservices. In fact, this helps to unify the way we solve common tasks. For example, imagine you need to work with money, countries, or run some transactions in microservices. Instead of every team writing its logic for these basic operations, we move these shared classes or utility functions into an internal library. This way, all teams use the same already tested code. By the way, the principles of organizing such libraries are very important. First, libraries should be stateless. This means they should not have their own database or state because this can cause problems with domain decomposition and make scaling harder. Second, libraries should include everything that is about shared functionality. This can be inter-service communication, logging, authorization, admin panel features, shared domain models, or general utility classes. This helps keep consistency and quality across the whole system. And one more thing, remember, this is only an approach, not a microservice pattern. Today we will look at the key patterns that help us build microservices architecture. First, we saw service registry and discovery, which let services find each other even in a dynamic environment. Then we moved to aggregator and API gateway, which give clients a single entry point together with features like authentication, monitoring, and caching. By the way, we also talked about BFF, where each client application has its own backend, optimized exactly for its needs. Next, we discuss proxy for safe integration with third-party services and sidecar, which takes helper functions such as logging, TLS, or load balancing. After that, we focus on CQRS, which separates read and write for better performance and scalability. And finally, we finished with the idea of internal libraries. They are not a pattern, but they help avoid code duplication and keep unified standards across the whole system. Okay, let's wrap this up with a short quiz. That's all for today. Thanks for listening and see you next time. Bye bye.